Welcome to another Ultralight Airplane Design video from the Ultralight Airplane Workshop. This is part 2B of a mini-series, part 2 of a larger series that is intended to design the main center spar of the UWS-4 ultralight airplane. And here, when I say ultralight, I mean an ultralight that meets the US FAA Part 103 regulations. What we're doing in part 2 is we're working on the distributed load across the wing of the ultralight. Now, there's lots of other loads that go on the center spar, like landing gear loads, the loads from the tail boom, loads from the fuselage, loads from the engine, but those are all point loads, at least where they attach to the spar. What I'm interested here is the distributed load. I guess I should mention there's a center section that we're working on now. This is the main design goal, but there's also outer panels of the wing. Now, the outer panels have distributed loads on them, but that outer panel puts a point load on the center panel, or the center portion of the wing. I guess I should mention when I say distributed load, I'm talking about distribution in the span-wise direction. So from the center of the wing out to the tip. There's also chord-wise distribution, but we're not worried about that yet. So in part 2A, the one before this one, I was working on figuring out how that load is distributed across the wing. And we got pretty far into it, but we didn't finish it. So this part is going to finish what we started in part 2A. So we were talking about additional load in part 2A. Now there's also a component called basic load, and we're going to get that hopefully in the next videos. Now, I ended that last video. Let's actually go back to those last few charts that I had on the last video. Kind of a reminder where we ended up. So here's pretty much where we ended in part 2A. We had distributed load here for 4 different wing planforms that I'm working on. And so we looked at kind of the center lift, and then we looked at the lift out here on the tips for the various planforms. So here's the lift out the tips. And I said that this extra lift out here for the rectangular wing, that's what the red line with the square dots is for the rectangular wing. For that rectangular wing, since it has the most lift out of these 4, that lift out at the tip has more leverage, a bigger moment arm. So that's probably going to cause the most moment at the root of the wing. So I would design for a rectangular wing. Now, I left off one sentence that I should have said and I forgot. That's if all the wings have the same surface area, which they do, and if they have the same span. Now, in this graph, they do. They go from 0 to 1, but in real life, they don't. The tapered wing would have the most span. The rectangular wing would have the least span. So when you start putting in the actual spans, I'm not so sure that this one is the worst case. So what we're going to do here in part 2B is going to figure out which one really is the worst case. So that's a sentence I should have put at the end of part 2A. So let's get to that. So here's a summary of the wings, which we looked at a little bit before. We looked at area, and we looked at span, and we looked at aspect ratio. So let's look at these. The rectangular actually has the least at 22.6, we've already talked about, and the worst case is the semi-taper at 27.4. Let's figure out which one of these really does have the most leverage or the most moment arm on that center spar. So the way we're going to figure this out is we're going to figure out where the center of pressure is for these wings. Now we'll first figure out what it is for a wing with span from 0 to 1, and then we'll multiply by our actual span, and that'll tell us where it really is out there in feet. And by the way, center of pressure is where if you concentrated all that lift on the wing down to one spot, in this case I really mean semi-span from the root out to the tip, where would that be? Now there is an equation in this technical report that we're using, and that's NACA Technical Report 2751. And this is the equation that's in the technical report. Now, like I mentioned, that lift distribution, that gamma sub A, there's 3 parts to this. And again, there's this part right here. This has to do with the planform of the wing. We got the part over here that has to do with an elliptical planform of the wing. And then we have an adjustment over here for sweep. Let's talk about this one first. This would be the center of pressure for an elliptical planform. So you multiply all this out, multiply by your C sub 2. Now remember we talked about C sub 1, C sub 2, and C sub 3 in the last video. and that would give you the center of pressure, or at least a portion, from an elliptical distribution. Now this equation over here is the equation for where the y position of the mean aerodynamic chord of a tapered wing would be, or even a rectangular wing. And lambda here is the taper ratio. And again, you're going to multiply that by c sub 1. And there's a way to calculate this j over here. We'll get to that here in a moment. So the problem I have is only one of my wings will work with this equation here. And that's the rectangular one. See, we have the semi-taper, we have the kind of modified rectangular one, and we have the multi-taper wing. This equation isn't going to work with that. It's not going to give the center of pressure for those three other wings. It'll give us the one for rectangular, but not the other three. So we got to figure out some other way of figuring out where the center of pressure would be, or better yet, where would the y position, the position from the root on out on the wing, where would that be for these other plan forms? And we can figure that out. So there's another equation for doing that. So here is the y mean aerodynamic chord for a plan form, a kind of arbitrary plan form that is made up of multiple tapered sections. And that works in my case great. So what you need to do is calculate the y position of the mean aerodynamic chord of each tapered section. So I've got 3 different sections in all my wings, actually 4 tapered sections on one of them, if you include the tip. So you take the first section, I'm going to call that the center section. You figure out where its mean aerodynamic chord is. Then you get the second section, figure out where its y position of the mean aerodynamic chord is, and so on. You multiply that by the surface area of that section, and you sum all those up. And then you divide by the sum of all the surface areas. In other words, the surface area of the wing, or at least the semi-wing. Once you do that, that gives you the y position of the mean aerodynamic chord of the whole wing. So in order to get the y position of one of the sections, you take the y position of the root of that section, and then you multiply that by basically that equation we just saw. So this is the y position, the mean aerodynamic chord of a tapered section, but we're only using a portion of the wing, a small portion of the taper. So this lambda here is going to be the taper from the root of that section to the tip of that section, not the whole wing, just that little section. And then you go multiply that by the span of that section. And then that gives you this y up here for each of those sections. You do that calculation for each one. And by the way, to calculate the surface area for a tapered area, that's this equation here. So the span of that tapered area multiplied by the quantity of the chord of the root and the chord of the tip added together divided by 2. So basically the average chord multiplied by the span. And once again, this is where spreadsheets come in really handy, because once you get this into the spreadsheet, then you just copy it into other cells and come up with other values. Spreadsheets really make all this so much easier. You don't have to do it by hand and be making mistakes. Okay, let's talk about how to do that j for the correction factor. This equation right here. And once again, there's a table back in the appendix of that NACA report 2751. And all you need to do is interpolate. So you need to know what the sweep of your wing is, that capital L lambda. So that would be over here, and then you just integrate to get the j. There's really not much to it. So if you have no sweep, j is 0.425. Here's the results of doing all those calculations for the 4 wings I'm interested in. Now you remember when I was looking at the end of part 2a, I said the rectangular wing looked the worst. That would be giving me the worst load or hardest load I had to design to for that main center spar. So let's take a look. So center of pressure, how far out is that center of pressure? From 0, that's the y star again. And we got 0.442 for the rectangular wing, a little bit less for the rectangular wing with a tip. Semi-taper is just a little bit further out than the rectangular, which is kind of odd. And then the multi-taper is just a little bit farther out, which makes me think I made a mistake, because I would expect this one to be out just a little bit farther. Let me go take a look at those calculations. This doesn't quite look right to me. There was a mistake in the spreadsheet. That's embarrassing because I did it on the video. Now, I often talk about in my videos that whenever you've got these calculations, whether you're doing it by hand or doing it by a spreadsheet, you need to do a sanity check to make sure it makes sense. Now, obviously, I failed to do that, so that's pretty embarrassing. But here on the video, which is the embarrassing part, I did check it and I saw that it didn't quite make sense. So I went back to my spreadsheets and I figured out what happened. On this rectangular wing, this number is pretty close to right. It's darn close to being spot on. And there are other places you can check online for a rectangular wing to see where that center of pressure is. 0.44 is fairly commonly used. But the equation I used to do this rectangular one, I copied and pasted on these other three, unfortunately, which means I left off the tip on these three. Now on this rectangular wing, the tip is pretty large, so it made a fairly significant difference. On these other two, the tip is much smaller. Since the tip is 0.6 of the root chord, tip is smaller, so it didn't make as big a difference. But essentially, adding the tip moved that center pressure out just a little bit on all three of these. But now, these look correct to me. At least the Y-star center pressure relative to each other. Center pressure with the tip should move just a little bit farther inboard than the rectangular, and it does. The semi-taper should be the farthest out, and it's at 0.429. And then the multi-taper should be just a little bit in, actually it should be between this rectangular with tip and the semi-taper, and it is. So at least that ordering is correct. So I now have finally done the sanity check, which I should have done a long time ago. Now, I mentioned that these numbers, this Y star, is a span of 0 to 1. When you go and multiply the actual span, things change. So I got actual span over here in this column. So when you multiply this 0.44 times the span, then you get where the actual center pressure is in whatever your units are. I'm using feet. So now let's figure out what the worst case is. So we're looking at 5 feet for the rectangular wing, just a little bit more with the rectangular. That's because the span moved out just a little bit more. So it went from being just a little bit under when we're doing Y star to being just a little bit past, a little bit higher when we've multiplied by the span. Semi-taper should be the farthest out. It's at 5.88 feet, and multi-taper should be in between, and it's at 5.7. So in this case, worst case scenario moved from the rectangular wing when we're just looking at 0 to 1 span to the semi-tapered one at 5.88. And that makes sense. At least that passes the sanity check. Well, that means that I should design the center section to be able to handle a semi-tapered wing. And if you remember right, semi-tapered is where the center section is the same in all the wings. But from that edge of the center section out to the tip, it's just a straight taper. And then it's got a little wingtip on the end of it. So I'll design it to handle a semi-taper, which I figured that would be the case all along. And then what I can do, if I have enough time, hopefully I will, I'll be able to build these various wings and do some testing on them to see if they behave the way the calculations say they should. I had mentioned in part 2A that you can get a first order, really rough approximation of the maximum lift of the wing, not the airfoil or section, but the entire wing, by taking the maximum coefficient lift of the airfoil multiplying by 0.9. That gives you a very, very rough first order, but I thought we could do better than that. Now, I found a reference to maybe get a better approximation, or at least a different one. I hope it's better. And it's in the book Theory of Wing Sections. Now, in my edition, I had the 1959 Dover edition, and that's on page 21, figure 16. It's estimation of the coefficient of lift, maximum coefficient lift, for an example wing. And it basically says that you take the lift distribution that you have, and you start increasing angle of attack until some portion of that lift curve meets the airfoil's maximum coefficient lift. And whatever that is, then you go back and recalculate what the lift for the wing is at that angle of attack, and that gives you the coefficient lift for the wing. And that's what I'm talking about here. So what we can do is we can calculate the local coefficient of lift of any section on the wing at any Y star from 0 to 1, 0 being the root, 1 being the tip. We take the lift distribution that we've come up with. In this case, I'm going to use the additional lift as an example. But whatever lift distribution we have, what we've come up with, we divide by the chord at a particular Y star divided by the mean chord. So you do this and it gives you the coefficient lift, local coefficient at some Y star. Now, at some point, as you keep increasing your lift, keep increasing the angle of attack, some part of that local lift distribution is going to hit a maximum, the maximum of the airfoil itself. And that's where the wing's maximum is going to be. So, and again, this is still an approximation. It's not perfect. It kind of depends on the stall characteristic of the airfoil, but it's, again, I think it's a little bit better than just multiplying by 0.9. So let's go through that. So that's what we're looking at here. We've used this equation. You're taking a lift distribution and then divide by whatever the chord ratio is, ratio of local chord by the mean chord. And that's what this is over here. So this is local coefficient lift as we go across the span. And I did it for the 4 wings I'm interested in. So the red one's a rectangular wing. This yellow one, which I'm sorry it's kind of hard to see, is a rectangular wing with winglet. The purple one with the triangles is the semi-tapered one. And then the green one with the kind of diamonds, actually those I guess are hexagons, is multi-tapered. And multi-tapered is the one I eventually want to build. I think it's going to be the best performing one. But you can see how this is different than the shapes we had before. You can see there's interesting little spike out here. So this is not lift distribution, this is coefficient of lift distribution. But it's going to behave a lot like the lift distribution where we multiply by angle of attack, and this will increase or decrease as we change that angle of attack. Now at some point, these curves will hit what the maximum coefficient lift is for the airfoil. And so whenever that happens on that particular wing, that's going to be the maximum lift coefficient for the wing. Then we come back through and recalculate what the coefficient lift for the wing is. So we got to be careful. There's the local coefficient lift and then wing, the total wing coefficient of lift. So here's an example of going through that. So this is the rectangular wing with the wing tip. And these lines are different angles of attack. Now this line right up here is the maximum coefficient of lift for the airfoil itself. So at some point we reach a angle of attack where the local coefficient of lift for the wing at some point meets that airfoil's maximum coefficient of lift. And that is right here. So that is at 20, really close to 22 degrees angle of attack. And as you can see where this CL max is for the airfoil, it's pretty close to 1.7. So where are these various 4 wings going to hit that maximum coefficient lift first? Well, for the rectangular, it's going to hit it right here in the middle first. So that's really nice because that means that the wing is going to stall here at the center first. And we like that because we like those ailerons to stall much later. That way, as we're approaching stall, start to get into it, the ailerons still have just a little bit of control to kind of keep us from rolling too far. Now, if we put too much aileron input, that'll stall an aileron. And the next one looks like it's going to be the rectangular wing. Again, it will stall in the center because it's going to hit that maximum first. Now, things are a little bit different down here. Look at this purple one. The purple one is semi-tapered. Right now, without any wing twist, it's going to hit a maximum right out here at about 0.6. So the stall is going to begin right out in this part of the wing. So that's undesirable. You want stall to be in here in the middle and then slowly progress as you increase angle of attack out toward the tips. So that's not good. And that's why you put twist into the wing so that you'll have lower lift out here because the twist will make a lower angle of attack out here and you'll start stalling here at the center first. So we would want to put enough twist in that this part of the curve would be down just a little bit, probably down around in here. Now what about our semi-tapered? Where in the past I said it's kind of approaching elliptical distribution. It's not that close, but starting to get there. So that's this green line. So, gosh, it looks like almost the entire first half of the wing will stall at the same time. Because that's almost flat right in here. So that almost entire thing will start stalling at the same time. And then it'll start progressing out toward the tip. That's probably not quite as desirable. It's not horrible, but it's not quite as desirable. So it might be good to put just a little bit of twist in the inboard part of the outer panel. So right in here, just a little bit of twist there, and that'll lower that, and then all the rest of this just a little bit too. By the way, an elliptical wing with an elliptical planform distribution, the local coefficient lift would be pretty much 1 all the way across here. I didn't draw it here, but that's essentially what it would be all the way across here. So you can see some of those wings are starting to get a little bit close to that. Rectangular is not even close. Rectangular with tips, not close. But you can see we're starting to get a little bit closer with this multi-tapered. It's really flat in the first half. And then, since I didn't do really an elliptical taper going out to the tip, it starts dropping off, which is okay. I'm okay with that. I don't mind having that tip drop off a little bit. Now that also tells me what might be worth doing. I could actually get this middle section right in here to drop a little bit in here. Just by changing the taper, I can reduce the taper just a little bit in here, and that'll make it drop off a little bit more. It won't quite match the rectangular, but it would drop off a smidgen more. So I could potentially get away without having to twist the wing if I change that taper. Actually, let's go take a look at that wing. I can explain a little bit better looking at it. Okay, here's that wing. Center section will not change at all. So I could make this chord just a little bit longer. And that will end up reducing the local coefficient lift out here in this area a little bit. And like I said, I'll get just a slightly closer to this kind of shape, the red one, the elliptical shape. That'll bring down this green line just a little bit right in this area. So that might be good enough to avoid have to add twist to the wing. So I'll probably experiment with that a little bit. So now we have an idea of what angle of attack that wing is going to have its maximum coefficient lift. And we know all these little dots out here for the local coefficient lift. So now we can figure out the wing's entire coefficient lift. And that's right here. The coefficient lift in the entire wing, see this big L, is the average of all the local coefficient lifts. So for a span of 0 to 1, which is what we're dealing with at the moment, that coefficient lift, see some big L, capital L, it's going to be the entire area underneath the curve of C sub L. So the entire area underneath this orange curve will give us the wing's coefficient lift. Now we can do that in a piecewise integration. We don't have to do like a big highfalutin mathematical integration. We can do it in a spreadsheet piecewise. And the way we do that is we go to each of these dots that we have here, and then we look at a span halfway to the next dot. So there's a dot right here, there's a dot over here where this dashed line is, and there's a dot over here where this dashed line is. So right here where this dashed line is one of the dots. So halfway to the next dot in each direction, that's going to be the span that we're going to be interested in, where this is the important part, this dot here. So to calculate the area, we're going to take this span, multiply by the coefficient lift. And then we're going to do that for each of these dots over here and add those all together. And that'll give us the area underneath the curve. Now I did that for all the wings. So let's take a look at the results for that. So here are the results. This column here is the maximum, I should have said max down here, maximum coefficient of lift for each of these 4 wings. So the rectangular is 1.43. Rectangular with a tip is just slightly larger. Now here's one of those cases where I say you should probably try to do a sanity check to make sure your numbers are right. I'm going to have to give a little more thought to whether this makes sense. And then the semi-tapered, this one does make a little more sense. It's a more efficient wing. Now remember, the semi-tapered doesn't have any twist in it yet. Things will change once you add a twist. It'll probably drop the maximum coefficient a little bit. But it is higher than the multi-tapered. Now let's see how this compares to that 0.9. I mentioned before in the last video, you take the maximum coefficient lift of the airfoil, multiply by 0.9, that gives you the maximum coefficient lift of the wing. Well, let's see if that's true over here. So that's basically what I've got over here. Now instead of 0.9, it would be 90 over in this column. This is basically percentage. So this will be 0.83, 0.86, 0.96, 0.95. And like I said, I'm going to have to do just a little more thinking if these make sense. Just off the top of my head, I would think that the multi-taper would be just a little bit better than the tapered, but I'm not sure. I'm going to think about that in a moment. So I think, though, assuming I've got these numbers calculated correctly, I like doing this, but it takes more work than just multiplying by 0.9. Well, that's the bulk of what I wanted to show in this part. I thought about adding a little bit more about setting up spreadsheets. Tell you what I'm going to do. I'm going to make a part 2C that talks about how I set up the spreadsheets for this. The spreadsheets are semi-complicated. It's not horrible, but there's actually more than one spreadsheet involved. So it seems a little bit clunky, a little bit difficult to use, but I want to kind of give someone who's actually interested in trying to do this a little bit of idea how to do it. And that also means I'll probably introduce interpolation, how to do spreadsheet interpolation there too. That'll be part 2C. And if you're not really interested in that, feel free to skip it. Won't hurt my feelings. I perfectly understand. So let's finish this up part 2A. I maybe should have included in part 2A, but it was getting really long. I try to keep my videos under 30 minutes. That one was around 34 minutes. It's hard to pay attention, at least for me, to videos that are technical, that are more than 30 minutes long. So I try to keep them under 30 minutes. And I think this one's quite a bit under 30 minutes. So part 2C, we'll be talking about spreadsheets and how to set those up, at least for this particular calculation. And then part 2D, finally, we'll get to basic lift. And that's going to include things like wing twist, aileron deflection, and flap deflection. Well, thanks for watching, guys. Till next time.